Hi, it's Terry Dennery of the MathWorks. So I thought about this one a little bit, and there was something that's been bothering me the last couple of days that I'll probably continue to work on, but I certainly, the fact that it continues to rotate in that yaw direction has been bothering me. You see it right there. The propellers are not even spinning. The vehicle is still rotating, right? So I want to kind of reveal the intent and just talk a little bit about yaw rotation, right? So this is what we applied for the torque. It's very symmetric, the same amount of positive as there is negative. So if you integrated that with regard to time, it should come to zero. Now, if torque is operating on a pure inertia, that means that at the end of this, the velocity should be zero, right? So anyways, I'm going to reveal even more. That essentially here's the torque that was applied. We see it right there. That's all that's going to drive the motors that connect to the propellers. And so we did one of these tricks I love doing, which is we're going to go from 0 to 90 degrees, right, in 20 seconds, and the rotation starts at 5 seconds, right? And you see, it looks like it was doing pretty well, but at the end, it just kind of continues to drift and rotate. And so, anyways, here's what I kind of came up with it as I thought about this some. And so this is in PowerPoint. And what I did was I just kind of superimposed these kind of torques. But the basic idea is that there is an aerodynamic torque associated with each propeller. It is going to be applied in a direction opposite the movement of the propeller. Therefore, it's going to be applied in the same direction the vehicle is going to rotate. And hence, it's this additional torque essentially generated and provided by the air that is going to lead to the additional rotation, right? And so I'll just kind of draw the conclusion, which I did state in the previous video, which is controlling yaw rotation is difficult. So I think I said in the previous video also that, and this is a general kind of awesome thing about feedback control, is it helps you deal with the things that you do not actually understand very well. And I'll just say that this one's probably going to push me, and perhaps I don't have enough time or even cleverness or intelligence to really kind of work through this one perfectly. But anyways, with that said, let's just kind of get into what we can do on yaw control, right? And so this one I'm going to just open up a model where I've done most of the work. The initial work just kind of came into, well, what do we want to happen? And so starting at 220 seconds, we will begin a adjustment of the torque that will take 20 seconds, and its goal is to turn the whole thing 90 degrees. All right. Now, the important thing I think I was able to state pretty well in the previous video, which is that the yaw control and thrust are actually, well, probably a better way to say it is that they're coupled, but certainly they are in conflict, and that those PIDs, they're doing essentially velocity control on the propeller. They just viewed these straight up torques we're trying to apply as disturbances, and they did a great job filtering it out, right? So from that, we realized to do yaw, you actually need to move through the mechanism of thrust control, right? And thrust control, of course, works great for pitch and roll. For R cross F, F is thrust, and more precisely, the incremental thrust. And we kind of talked about that to get the torque, let's say, that will rotate it about its y-axis. I think that's what we call roll. It means give a little bit of positive thrust on the X end, or I'll say the positive end of the X beam, and a little bit of negative thrust on the negative end of the X beam. I might even have the signs wrong on that, but it's that idea that the incremental thrust is equal in magnitude but opposite in direction. Why pitch and roll are almost, I'll say, by definition, certainly by the design, they will be decoupled completely from the thrust control, right? That they contribute zero to the thrust that's going to ascend the vehicle. So, anyways, but it's not quite so easy with yaw, right? and it's that aerodynamic additional torque, which at this point is kind of preventing me from doing much better. But here's what I came up with, right? And it is this idea that I can convert torque into a delta thrust, and that delta thrust gets added to what's ultimately spawned out of the ascension thrust, to kind of do that kind of rotation. And right now, and I did make the argument that, well, roll and pitch are the same thing, but if I was going to do a true vehicle, I'd put in a fourth one, and there'd be a separate one for roll and a separate one for pitch. But anyways, here's kind of what I came up with. So we open this up. It's that idea that torque comes in. And this is kind of why I needed to get to this elaboration, is that it's a square thing. It's the square of the propeller speed. But the torque comes in. This is ultimately going to be torque that's going to go in the propeller. And so we have a minus sign. We divide it by 4 because there's 4 propulsion units. And we divide it by propeller inertia, and then we integrate it, right? And what we're kind of doing here is we're unpacking the thrust and getting it back to a propeller speed. So we're essentially adding apples with apples right here. And then we square that speed. Yeah, so this is kind of the, and then we multiply it by the lift coefficient. And then we ultimately subtract that thrust so that what we're really providing will be the incremental thrust associated with Z rotation. And I think I'll just run it, and we'll kind of look at it through that. Let's get it going. So it's certainly hitting the 0 rotation quite well. We're certainly doing very well on elevation throughout most of this. But let's get the rotation back up there. Seems like the model runs a little more slowly right now. Not exactly sure why. It could be the additional integration that we're doing in this. But yeah, I'm not really sure why. Okay. So that's kind of interesting. What we're really observing right here is kind of well, it's not really a limited thing, but the idea if you're going to do a measurement on angle and not include the wraparound, so they can go beyond 360 degrees, that we're simply seeing it through the lens of 180 to minus 180 degrees. So this simply says it rotates quite a bit, and we'll go take a look at that now. So. Right. Let's see, 115, enter. Just going to remind you of a few things. There's our roll and pitch, which we are perfect at. That type of control. But at 220, and so bring ourselves to 215, so that's 5 seconds before the yaw rotations will begin. And we see it start rotating. And the perfectionist in me is a little bit kind of, I'd say, still kind of bothered. I can't precisely control it, but I am encouraged that I do have a means to apply torque, and at least in the direction and probably close in magnitude of what I'm trying to do. And it's possible I could do a little bit more aerodynamics work to be a little bit more precise in that, have these additional aerodynamic torques not compensated for properly. But I want to kind of get back, kind of indicating the direction where our next video will be. At least 10 videos back, we put this little feedback loop in, and we essentially asserted that this is going to be our flight controller. But look at that, we're still terminating it, right? And I'll just say that as we unpack this and employ feedback properly, I think that we can do a little bit better on the yaw, okay? Because feedback really is helpful and very, very useful. I've been somewhat intentional of not going there because we're operating very theoretically throughout this series of videos. And I am emphasizing this idea, the better you know that system, that there are choices you can make in how you're going to formulate your control of that system. And if you really did have perfect information, you would not need feedback. Well, of course, you always are in the situation where you do not have perfect information, and certainly the wind will blow different every day, and people of different weights will get on that quadcopter or will load different weights on it, and therefore, things are always be a little bit off. And so we'll move a little bit more into the feedback and employ it a little bit better in probably the next video. And then just kind of commenting on the fact that yaw is hard. Well, most airplanes can't yaw at all, and if they do, that's kind of a problem. Maybe they can yaw a little bit, but for the most part, you know, turns are going to take place because you're going to roll a little bit and then you're going to pitch, in that new roll configuration. So between roll and pitch, you have incredible ability to kind of change direction into any direction you need. Um, so I think that ultimately I'm still kind of incredibly impressed by how clever the quadcopter is and the remarkable capability it does have. That we can move it in X, Y, Z, any direction we want. We can roll it, we can pitch it, and we can even yaw it a little bit. And we'll see how feedback will help us out in the upcoming videos. All right, thank you.